of NPTEL TA live discussion. So today I am going to discuss about the mathematical modeling and then mathematical and how to I mean for mathematical modeling for mechanical system and electrical system. That is how we can derive a system by some kind of differential equations. And then I'm going to talk about how we can define the transfer function from a state space model. So since transfer functions is though a very primitive method for a control system, because we are now discussing on the advanced control system which is based on the state space model. But there are few companies, I mean there are industries which basically do the controlling part, I mean, based on the transfer function model, such as, I mean, PID control method is basically based on the transfer function model. This is basically one of the pole placement kind of thing, right? So we will see that how transfer functions can be defined from a state space model, and then there are another topics which is Leverrier algorithm, so which is also known as a Faddeev-Leverrier algorithm. So this algorithm basically used when the system dimension is very high, and it is I mean in previous era the computation is not that much developed one. So it is very difficult for them to find out the inverse of a matrix if the dimension is very high. The computation is very so therefore it is very computationally expensive. For that case, this algorithm has been designed. So here we do not need to do any kind of I mean any kind of inverse kind of technique. Like we do not need to find the adjoint of the matrix or the determinant of matrix explicitly. So here there's a procedure by which we can find out the inverse of a matrix without finding the adjoint of the matrix or determinant of the matrix explicitly. So we will see how this algorithm works. So before I'm starting with starting the discussion, I just want to know, is there any kind of doubt? Do you have any kind of doubt? So you can ask me. I'll start with that. So if you have any kind of doubt, please, I mean, feel free to tell me. This person is so assuming that you have no doubts, so I'm just start with my. So I hope my yeah, my page is visible, right? So first of all, I start with a state space model of our mathematical model of a mechanical system. So we know that normally in generally mechanical systems are defined with a, since we are here, we are basically talking about the linear control system. So the all the things that I'm going to discuss over here is will be linear in nature. There is a no non-linearity of the system. Okay. So in the mechanical system, generally we there are two kind of things. I mean, using the just a minute. Yeah. So in kind of mechanical system, so in general we can define any mechanical system using a mass spring and damper kind of system. So as a control engineer, we our work is basically is to design a controller or design an observer to observe the state of the model or to control the states of the model, right? So for that case, we need a dynamic equation of the system, like how the system dynamics works. So for that case, we need a mathematical model. Let's say we have a robot, we have a manipulator. So we need, so let's say there is a manipulator. Do you, I mean, you have idea that let's say we have a manipulator which is only one hand. So this is the base of the hand robot. Okay, so let's say this is a base, and here the one actuator is here. So this is basically rotating part, and this is the hand of the, I mean, this is the robot part, which basically rotating. So the thing is, so we need to control. So our controller should be, let's say we have one actuator. So this is actuator. So we need to control this actuator so that we move our robot accordingly. So for that case, we need to know the dynamics of the system. Okay. So let's start with a very easy thing. So we know that every mass exert a force. Okay. So if this is a force applied to the mass, there is nothing is attached, any spring or damper is attached to the system. So if this is the mass and I'm applying the force to the mass, so because of the inertia of the mass, we know that the F should be all the force acting on the mass is equals to m into a, and this is, let's say, displacement. The mass is basically displaced from this position to, let's say, in that position when I apply the force. So this is basically the displacement. So when I apply the force, this mass m displaced by x distance. So therefore, according to Newton's law, the force acting on the mass is basically F is equal to ma. And what is A? A is basically acceleration, which is d2x by dt2. And if there is a spring attached to the system, so if there is a displacement x, so this is the original position of the spring, and after applying the force, less the spring displace this much. Okay, so this is F. So this force applied to the spring has a constant. If this spring constant is, let's say, k, so this spring is basically linear in nature. I'm not talking about any non-linearity about that, because there are non-linear spring whose displacement is not linearly dependent on the force. So here I'm talking about the linearity of the spring. So if the force applied to the spring is basically proportional to the displacement, so we know that F is equals to kx. This k is a spring constant. And for a damper, sometime it is called dashpot. If I apply to the system, so let's say if this is a displacement, after applying force, this is the displacement of the damper, and it has a coefficient, let's say b. So the force is basically proportional to the directly proportional to the velocity of the system, which is F proportional to the x dot or dx dt. So it is F equals to v dx dt. Now right now I'm going to take an example. So let's say I have a system like this. So let's say this is a system. I'm taking a double mass spring system. So here this is M1, here this is M2. Okay, now there is a spring in between them, there is a damper in between them. Okay, now here is the spring over here. There is another spring over here, and this is attached to something. This is attached to something. Okay, and the force displacement, this is x1 and this is x2. Okay, and the force is applied on this is, let's say this is a force that is applied on the Q, that is applied on M1. So the spring constant, this is a K1, let's say this is B. No, this is not K1, this is K1, this is K2, this is K3. Okay. So first of all, we can do this, we can derive the differential equation of this system, this kind of double mass spring system, by using a free body diagram. And so we can basically derive the differential equation of mechanical system either using free body diagram, which is FBD, or nodal analysis. So nodal analysis is basically effective when the system is very large. Means there are so many degrees of freedom. Let's say instead of this two double mass spring system, there are, let's say six mass damper system, mass spring damper system is there. So when the system order is very large, in that case, it is very easier for the control engineer to design a system equation, system differential equation using a nodal analysis. So nodal analysis is basically, this is basically electrical circuit representation. This is basically analogous to electrical circuit representation. This is basically analogous to okay. So right now, first I'm going to do this using free body diagram. So here the mass one. So I'm just write down. I'm just write down the drawing the forces acting on the mass one, M1 and M2. So first thing is applied on the M1 is basically this is, so here is applying, this is the K1. This is, let's say F1 is the this force. This is the force U applied in this direction, and then this is force, let's say F2, and this is force F2. This is due to this K2. Due to this K2, you get the mass M1 is basically the force acting on the mass M1. F2 is acting on the M1 is due to K2, and F3 is due to B, that is the damper. Similarly, this is the force, that same force. Remember, this force, let's say I'm just writing down this F21, F31, F22, and F32. So you see that the spring K2 and the damper B, these two basically attached with M1 and M2 both. So the net, so the similar force will exert on M1 and M2 due to K2 and B. So this F2 and F3, F21 and F31, sorry, this F21 and F22, these two are basically the, this is K3. So this F21 is basically equal in nature but opposite in direction. The magnitude of F21 and F2 are basically equal, and the magnitude of F31 and F32 are equal. Okay. So now what are the forces that is acting on the system? So F1 is a force due to spring, let's say K1. F1 is the force due to spring K1. So what is the force? I'm considering the, let's say, considering this is the positive force and this is the negative force. Okay, let's say I'm considering this thing. Okay, so force due to spring K1, what would be the force? Since the force is basically direct proportional to the displacement, and for the first case, m1 is displaced x1 by x1, and m2 is displaced by x2. So what would be this? Minus k1 x1, and k1 is the spring constant. Okay, F21 is force exert on m1 due to spring k2. So what is the basically displacement for this case? For k2 case, what is the displacement? The displacement is basically x2 minus x1, right? This is the displacement. Right, this is the displacement for this k2 case, because for k1 case there is a displacement is only, is my screen is moving? Hello?
No, sir.
It's not moving, right? Uh, and just just 1 minute. Okay, now it's visible, right? Now it's visible, right? Yeah.
Yes, sir, it's visible.
Yeah. So basically, for the K2 case, for spring K2 case, the displacement is x2 minus x1. So the force would be, and it is acting on this direction, acting on this direction. That means the positive direction. So it is K2 into x2 minus x1, and let's say F31 is a force exert on M1 due to damper or dashpot, let's say B. So what would be the force? It is basically the directly proportional to the velocity of the displacement. So this is B into x2 dot minus x1 dot. So we know that summation of all force acting on M1 is basically M into d2 x1 by dt2, right? So what are the forces? The forces are K2 is basically, let's say F21, The forces are F21 plus F31, F21 plus F31 plus U minus F1. Okay. And just draw the figure over here. F21, F31, this is F1, and this is U. So what are the forces? M1 x1 double dot is equals to K2 x2 minus x1 plus is B x2 dot minus x1 dot plus U minus K1 x1. So what I will get? M1 x1 double dot plus B. If I move it over here, it will be x1 dot minus x2 dot instead of x2 dot minus x1 dot, right? Plus k1 x1 plus k2 x1 minus x2, that is equals to u. So this is the first equation. So this is my first equation. This is equation number 1. For the second case, what is basically my free body diagram? My free body diagram is this is M2. The forces acting on this is F22, this is F32, and this is F3. Okay. So the forces, so F22 is basically, what is F22? This is minus of K2 into X2 minus X1. So what I say, F22 and F21, their magnitude are equal, but they are in opposite direction. So that's why, because of this opposite direction, this minus is over here. F21 is basically, sorry, F32 is basically minus B into X2 dot minus X1 dot, and F3 is minus K into X2, sorry, K3 into X2. So what are the forces? M2 into X2 double dot is equals to minus K2 X2 minus X1 minus B X2 dot minus X1 dot and minus K3 X2. So that my third equation would be M2 X2 double dot plus B X2 dot minus X1 dot plus K2 X2 dot minus X2 minus X1 plus K3 X2 is equals to 0. So this is my second equation. Okay. So up to this point, is it okay to everyone? I mean, there is anything that is difficult to understand for you?
Sir, first when you are writing that there you have given it as K3, sir, in the free body diagram. Instead of F3, I think so it is you have given it as K3 in the initial point, I think so.
Oh, okay.
So there
Okay.
it
Yeah,
should
yeah,
be
yeah, 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 should be actually, yeah. Okay. Otherwise, it is okay, right? It is okay for everyone. So I'm just moving to the next part. Like, okay, I have gotten the dynamics equation of the two bodies, two mass bodies, M1 and M2. And since we have two different displacement, so there's a first displacement. So this is displacement number 1, and this is another displacement number 2. And there are two bodies. So obviously we know that there will be a fourth state, right? Which are x1. Let's say I'm considering the states. I know the normally we use x1, x2 as the state, but here since already I have using the I have used this x1 and x2. So instead of x1, x2 as a state, I'm using p1. So p1 is, let's say p1 is equals to my state x1, and p2 is equals to my state is x1 dot, which is basically p1 dot. And p3 is basically I'm considering as the x2, which is the displacement of second body. Displacement of second body, and p4 is equals to x2 dot, which is p3 dot. So now we have to find out the value of x1 double dot. That is, we have to find out the value of p2 dot, which is basically x1 double dot, and p4 dot, that is basically x2 double dot. These two equation we have to find out. So from here we know, if we find out this x1 double dot, we will get this equation, that is m divided by this whole term will move to the left hand side, move to the right hand side, and divided by m1, we will get minus b by m1 into x2 dot, sorry, x1 dot minus x2 dot minus k1 by m1 x1 minus k2 by m1 x1 minus x2, and plus 1 by m1 u. So what should we do? We transfer into a state model form, that is p2 dot is equals to x1, take x1 part as a common, k1 by m1 plus k2 by m2 into p1 minus, sorry, plus k2 by m1 p2, sorry, p2 this is p3 minus b by m1 x1 dot, which is p2 minus b plus b by m1 x2 dot, which is p4 plus 1 by m1 into u. So up to this point, everything is clear to you, right? Now similarly, the x2 double dot is minus b by m2 x2 dot minus x1 dot minus k2 by m2 into x1 x2 minus x1 minus k3 by m2. This is x1, sorry, this is x2. So what we get, p4, sorry, p4 dot is equals to minus k2 by m2 plus k2 by m2 into x1, x1 means p1, minus k2 by m2 x2, x2 means p3, plus b by m2 x1 dot, which is mean p2, and minus b by m2 x2 dot, which is p4, and minus k3 by m3 is, I can do this over here. This is minus k2 by m2 plus k3 by m2 into p3. So therefore, I'm sorry. So therefore, this p1 dot, p2 dot, p3 dot, and p4 dot, this will be equals to, the p1 dot equals to p2, that is 0, 1, 0, 0. p2 dot is equals to minus of k1 plus k2 divided by, this would be, this is my mistake, this would be m1, m1 P1, then P2 is minus B by M1, P3 is K2 by M1, and P4 is B by M1. So P3 dot equals to 0, 0, 0, 1, and P4 dot is equals to K2 by M2 minus K2 plus K3 by M2. Ah, I'm sorry. This is B by M2 minus K2 plus K3 by M2, and this is minus B by M2. P1, P2, P3, P4, and plus here U is connected to P2 dot, so it will be 0, 1 by M1, 0, 0 into U, and let's say I'm considering the output is X1, output basically are X1 and X2. So in that case, the output equation would be Y is equal to 1, 0, 0, 0, 0, 0, 1, 0. This is X1, sorry, P1, P2, P3, and P4. Okay, so this is clear to everyone, right? I hope I'm audible to everyone. Is there any
Yes, sir.
doubt?
You are audible, sir.
So is there any doubt up to this point, or do you have any other doubts so which you can ask?
Sir,
No, so
okay, madam,
Yeah.
you continue, ma'am.
No, sir.
yeah,
Okay, that's good. And I hope I'm, yeah, pronouncing your name correctly. Sanup, do you have any doubt? I think you are basically asking to
Yes, sir.
something.
The
Yeah.
thing like, sir, you told the nodal analysis is
Yeah.
used for the method which we are using for this particular thing, sir.
Hmm.
Sir, my basic question, like for a mechanical analysis, whether we will not be considering the mesh as well as these or other analysis. Only nodal analysis method only will be used. Correctness, sir.
So what I understand about your question is like that nodal analysis is useful when the mechanical system is very large. I mean, there are lots of masses over there, lots of dampers over there, lots of springs over there, and it is difficult to draw the free body diagram. In that case, in that scenarios, let's say if you consider a system with a like inverted pendulum system, which I have shown to you previously there. So this is basically an inverted pendulum system. A pendulum means there is a one hand and it is attached with the base, an inverted one. So this is very easy to make, easy to create the mathematical model of this system. Now, instead of this mathematical model, instead of this one link, let's say there are 6 links attached to the another 5 links is attached to this one. So in that case, I mean, obviously that system will become a non-linear system. This is not a no longer a linear system. This actuator, this inverted pendulum system is no longer a linear system. First of all, it is a non-linear system. So we are basically assume a few things so that we can linearize it. Now, if there are lots of things attached to it, so it is very difficult for the control engineer for us to design to get a mathematical model of the system. If you if you draw the free body diagram of a very complex system, you can do that. If you know the free body diagram very well, then you can separate the each part and draw the forces acting on the each part, and then find out this using this Newton methods. You can find out the dynamics of the equation. That is well and good, and you will get almost exact result of the I mean almost exact representation of the system. I mean, using nodal analysis you also get the exact representation, but the nodal analysis basically, it's as I've said, it is analogous to the electrical circuit. So when the system is very complex, it is easier for us to visualize the things. It is easier for us to visualize the force acting on the each system, how it will work, and then it is easier for us to design the dynamic model. So there is nothing wrong with the nodal analysis or nothing wrong with the free body diagram analysis. It is just for us to make things easier for us. Okay. So I hope I have answered your questions, or your question is something
So the
else.
question was like, sir, we are having the nodal analysis especially for this mechanical system, like otherwise
Yeah,
free body diagram. So
yeah.
apart from that, when I'm going through some other books and all, they have given like some loop analysis, mesh analysis, lot of things was there.
Huh.
So whether like that is not relevant to the mechanical system, am I correct, sir?
I mean, you have seen a loop analysis applied on the mechanical system as well. Loop
No,
analysis
no,
on
not
mechanical.
like that. No, not like that way. When I'm just going through that different books, they have told
Okay.
different methods like that is there. So my doubt
Hmm.
is that the loop analysis or these all things, whether it is not applicable for mechanical, correct, na, sir?
Loop analysis, I don't think it is applicable for mechanical system. I'm not very sure, but I think that nodal analysis is appropriate, but I literally don't know the whether the loop analysis will. I've never seen any book or anywhere where the mechanical body, the I mean any dynamical equations of a mechanical body get using this loop analysis. So I don't think the loop analysis is used very widely, or if they use, I don't think that they use very widely.
Okay, sir.
So I think the best method is, I would say, because I prefer this. It is not a general thing. I prefer the free body diagram method because this gives you the clear vision on how many forces acting on each parts of the system. So it is very easier to understand. It is easier for me. It's not the general statement. It is my view that the free body diagram method is very much easier to understand. Otherwise, you can do the loop analysis. So I'm not going to discuss about here the nodal analysis here, since I mean, you have all of you have the idea, right? What is the nodal analysis? So it is basically just I'm just drawing the circuit. I'm not going to do any kind of thing. So first, the node basically over here we discuss, we choose the node number of node based on the number of displacement, right? As you have studied, the number of node is basically the number of displacement. So this is x1, this is x2, and this x. Sorry. So what we do, the mass m1 and mass m2 is attached to the displacement with respect to the reference. This is basically the reference, and we know the force is acting on mass 1. Force is acting on mass 1. This is basically my u, and here in between my displacement 1 and displacement 2, this 2 between mass 1 and mass 2, we have one spring attached to there, that is a k2, and here is a damper or dashpot, that is b, and here another spring is attached to there, which is only k1, and here another spring attached to there, which is only k3. So this is now become the system that whichever the system that I have shown previously. This is the node representation. Now, if we what we have to do, we have to apply the apply it on node 1 and node 2. That simply that KCL KVL what we do in a network theory. So this is U is basically equals to M dx1 and d2x1 dx1 double dot plus k1 x1 plus k2 into x1 minus x2 plus k2 plus b into x1 dot minus x2 dot. And similarly, when we apply this node analysis on k2, it is basically m2 x2 double dot plus k3 into x2 plus k2 into, please mute the someone please mute your thing. So yeah, k2 into x2 minus x1 and then b2 into b into x2 dot minus x1 dot, and you will get the whole equation, and this is the representation of node analysis. Now I'm going to discuss let me just I'm not going to detail about this, just give another example of, so this is basically a quarter car model. Quarter car model means this is the 1/4 of the car model of the car model. So this is also active suspension car model. Okay. So why it is active suspension? You will see. So let's say if this is a mass of the body, okay, and this is the mass of the suspension. So there is attached a hydraulic actuator over here. Because of that, because of this hydraulic actuator, this is called active suspension. There is another one spring, let's say K1, dashpot, let's say B1, and there is another spring attached to the suspension called K2, and this is rod. Okay. So this is the one, matlab, this is basically the representation of one wheel, and there is a mass attached to that one wheel. So in that case, there will be, if you want a full car model, so that will be, this system is basically a force system which is acting on parallel, right? So this is the displacement. Let's I call this S1, this is S2, and this is SR. So S1 is the displacement of the body, which is upward. S2 is the displacement of the body, which is upward, and SR is the force exerted by the rod. So this will be neglected. So SR will be neglected if rod is smooth. So if there is no up and down, I mean, road is very smooth. There is no, I mean, there is no potholes or any up and downs on the road. So this SR can be considered as a as zero. Otherwise, this SR basically a disturbance that is added to the system. So right now, what we have seen, so in that case, we have seen that there is a system which has a system matrix. This is a system matrix, this big matrix 4 cross 4 system matrix, and this is the input. So this input is attached to the input is applied on the system. So if I apply the force, the body will move. So basically U is the controlling force, right? Now in this car system, here another disturbance is added over there. So now if we do this using a free body diagram, what we'll do, so this is, I'm just writing down the free body diagram, and I hope you will definitely get the dynamics equation of the system. So this is M1 and this is M2. So the displacement, this is the displacement S1 and this is the displacement S2. Okay. So what are the forces that acting on MB? Sorry, MB, and this is MS. So what are the forces that is acting on MB? So MB acting on is, this is the actuator force U. So let me write down all the parameters over here. So F is basically the hydraulic actuator. Okay. So so the force exerted by the F is upward. So this is the upward direction. So this is basically I'm considering U, and other two forces acting on MBA are, first of all, let's say F1, and this is F2, right? This F1 is due to this K1 and F2 is due to this B1. So similarly, MS, that is the suspension body, it also exerts three force. Okay, the one force is this U. Just a minute. Yeah. So this will exert F1. This F1, this F1 are similar. This is F2, and here this is F3, and here is U. Okay. So the F1, let's say I'm calling it F1 prime, F2 prime. F1 is the force exerted by spring K1 on M1, sorry, MB. F2 is force exerted by dashpot B on MB. F1 dot A prime is equal to force exerted by spring K1 on MS. Sorry, this would be spring, and F2 prime force exerted by dashpot B on MS, and F3 is a force exerted by spring K2 on NS. So applying the similar procedure, so you will get, obviously there are two masses over there and two displacement. So number of states will be 4. So this would be, let's say, x1 dot, x2 dot, x3 dot, x4 dot. This would be the system matrix into x1, x2, x3, x4 plus some input vector into U, and plus something, some disturbance vector into SR you will get. So this kind of structure you will get. So I hope you can do this by your own in as a, I mean, homework or something. You can try this kind of thing. So now next I move to the next segment of our of my this discussion, which is uh, the transfer the modeling of armature control and the modeling of DC servo motor. So first of all, let me ask you one thing. Do you have any doubts on the? So I will not then discuss the whole thing. I will just clear the doubts and then go to the next segment. So do you have any doubt on this DC servo motor of armature control or field control DC servo motor? Do you have any kind of doubt over there? I mean, so that I can discuss. Otherwise, I'll move on to the next segment. So you have no doubt, that means, right?
No doubt, sir.
So no doubt regarding that armature control DC servo motor and field control DC servo motor transfer function, right? I mean, is it okay? So I'm not going to discuss that part, right? Or should I discuss it a little bit? What you like to say?
Sir,
Okay.
you can just give a small, brief comparison.
Okay. So brief
Very
comparison.
brief.
Okay. So first thing is, what is the I mean, what is beneficial for us? I mean, what is beneficial for us to for armature control DC motor or field control DC motor? Which part is more stable, which gives a more stable dynamics of the system? Okay, so DC motor, in case of DC servo motor, so the servo means basically there's some kind of like position velocities. We are basically talking about some kind of position and velocities, some kind of things. So we define a transfer function of DC motor from two perspective as a position. So the applied input voltage and position of the system, position of the motor, or the velocity of the yes, the velocity of the motor, and that is the speed of the motor. Sorry, velocity is now, it's the speed of the motor and its input, applied input to the system. So if theta is the position of motor and theta dot is basically the speed of motor, and in armature control, so this is the diagram of a motor. So I draw this RA and LA. These are basically the armature resistance and armature inductance, which is basically inside over here. So I draw it outside just to make it clearer. Okay. And here is the field. Okay. So in armature control.
Sir, can I interrupt, sir? Sir, you can just
Yeah.
give a brief only, sir.
Okay. So brief.
No,
I'm
no
just.
need. Sir.
Okay. So brief in the sense. So in armature control, basically we keep constant the flux of the system. We control the input voltage so that we get this back EMF, and we can control the IA. That is basically we just control the IA so that we can control the speed of the system. Then flux is constant over here. And in field control method, there is we try to constant this armature current. Okay, we try to constant this armature current. That means this is basically field controlled. Sorry, this is basically armature controlled method, and IA is kept constant. That is armature current is constant for field control. Now, in case of field control method, sorry. So in case of armature control method, you will see if we find the theta s, I'm not going to in details, but if we find the theta s, you will get some theta s by es, sorry, theta s by VAS, because I'm over considering a VA. So you will see some, let's say k divided by this here, the third order system. You will see the third order system, right? Or I just write down the note whole thing. Yeah. So it is k divided by s into sj plus b into ra plus sla plus s into k into kb, or let's say km. So you can see this is a third order system, right? So third order system is basically an unstable system. So in the first class, I have shown to you, let me take you to the first class. So in the first class, I have shown to you, if we added a pole to the system, if we add a pole to the system will leads to the instability, right? So here you can see the system has a two poles. All the root locus lies on the left hand side of the complex plane. But once I add the third pole to the system, there are some certain gain k is over there. There are certain gain k is over there, because of which the system will become system will become unstable. System will leads to the instability, right? So here, in case of position control for armature, in case of position or I mean transfer function of positions with respect to the input voltage for armature control method, you will see that this is basically a third order system. Okay, so that means our system will leads to instability, but we can approximate, since this Ra is greater than this La, the value of the armature resistance is very much higher than the armature inductance, so we can neglect this La term. So if we neglect this La, this will become, this part will become 0, and now this is become a, this theta s by Vs will now become a second order system. This is the approximate, not exact, remember. Okay, this is now become a second order system, and we know that second order system, there is a I mean in second order system it is a stable one, root locus. If the all the values, all the coefficient in the denominators, in the polynomials of the denominators is positive, then the system is stable one, and root locus will lie on the left hand side of the complex plane. And if we consider speed versus the transfer function with respect to VAS, this, so this term is, now whether you consider LA or not, this term is second order term. So whether you consider LA or not, that does not matter. When we find out the transfer function, the speed of the motor with a armature input voltage, it will always gives you a second order system, right? But in case of field control method, if we consider the field control, so in field control, here we cannot, the main problem over here is we cannot neglect the value of LF. So if we neglect the value of LF, so there is nothing about the field, there is nothing about the flux, and the motor will never, basically motor will never move, never run basically. Okay, so that's why we cannot neglect LF for field control method. So that's why in case of field control method, the theta s by VA, sorry, theta s by, let's say, VFS is always a third order, always gives a third order model. So this may leads the system to instability for some values of gain, motor gain. But here speed by VFS is a second order, gives a second order model. I'm not writing down the model, I'm just clicking over here. Second order model, which is stable one. And if you draw the block diagrams, because here in case of field control method, there is no back EMF. Okay, because we considering that there is a IA is basically considering as a constant term. So we are not considering any kind of back EMF kind of things, because IA is considered as a very small and it is considered as a constant term. So that's why, since in field control method there is no back EMF kind of such things, so you will see there in the block diagram, you will see there is no feedback loop over there. But in case of armature control method, since there is a back EMF plays a important role in armature control method, so there is a feedback loop over there. So that's why I mean field control method is basically preferable for a smaller motor, whereas the armature control is preferred for a larger kind of systems. Okay. Now move to the next segment. The next segment says is determination of transfer function from the state space model. So state space model. So since as I have told previous, so if we are working on the state space model, what is the need to transfer the state space model in the transfer function? So we need to transfer the state space model into transfer function, because sometimes we need some kind of, I mean, there are various industries, they prefer to use the PID control techniques for large machinery. They prefer to do this. And for that case, they need this lag compensator, lead compensator, lag lead compensator. So basically, they need a PID controller for that. And basically, and this PID controller is based on our this transfer functions model. So that's why we need a transfer functions model. So a short version. So the system state space is x dot equals to x plus du, and y is equal to cx plus du. Now we take a Laplace. Transformation, and what, considering that all the initial conditions are zero, because that is when we talk about the transfer functions, we first thing that we are considering is our initial condition should be zero, right? So this is xs. I am moving this x to the over here is equals to VUS. So what I get, xs is equals to Si minus A inverse into BUS. And if I consider this YS equals to CXS plus BUS, so what I will get, I would get C into Si minus A inverse into B plus DUS. So the transfer function is YS by US. This is C into Si minus A inverse into B plus D. Okay. So here the problem is to find out the inverse. Okay. So here in inverse, in case of this inverse, as you know, this Si minus A inverse is basically the adjoint of Si minus A divided by determinant of Si minus A. So what is adjoint? So for, let's say, 2 cross 2 matrix, if A is, so this is basically R means I'm considering that all the elements in the matrix A are real. Okay, so the R stands for real. So let's say A is belongs to 2 cross 2 real number. So A is, let's say, A11, A12, A21, A22. Okay. So if A is invertible, it is very easy to find out the adjoint as well as the determinant of the matrix. Now, if A is now become a 4 cross 4 matrix or 5 cross 5 matrix. So it is very difficult to find out the inverse of this Si minus A, because finding out the adjoint of Si minus A is very difficult, because in A adjoint, if finding out the adjoint, we need to find out the cofactors of every elements of the matrix. So the here, if we need to find out the adjoint of A, so what we need to do is cofactors of A11, which is A22, cofactors of A12, which is A21, cofactors of A21 is minus A12, and here is A11, and then I have to take the transpose of this matrix. So then I will get the adjoint A. So it is very easy for 2 cross 2 matrix, but for when I'm doing the 3 cross 3 matrix, it is quite difficult. So that's why, and in the previous time, there are no such a computational programming language, such a high computational programming language which can do this kind of operation, inverse operation for higher dimensional matrix. For that case, two mathematician comes forward and gives us this algorithm, which is also known as this Leverrier sorry Leverrier algorithm. Sometimes it is also called only the Leverrier algorithm. Okay. So what this algorithm basically says, it says, okay, we do not need to find out the cofactors and all kind of things. It is very much messier. So let's say we know that we can represent adjoint of, since I'm talking about Si minus A, so let's do with that. We can represent this adjoint of Si minus A using this format. Okay. Using this format, and determinant of Si minus A is basically using this format. So they basically, this method is basically the recursive approach to finding out the coefficient. So this method is basically the recursive approach to find out the coefficient of characteristic equation. So what is the procedure? The first thing, okay, so if we find out the values of a1 a2 up to an, and find out the values of p1 p2 up to pn, then we can just divide these two things, because this term is a constant term, we can divide it, and this is a matrix term, so we can get the inverse. Okay, so how it is possible? The first thing they said, okay, consider p1 as a so p1 is considered as the I, and a1 is minus trace of A. So TR is basically, this is basically trace. So trace is basically the summation of all the diagrams of a matrix, square matrix. Okay, because we cannot take an inverse of a rectangular matrix. definitely. So P2 is considered as A into P1 plus A1 into I, and A2 is equals to minus 1 by 2 trace of P2 into A. P3 is equals to A into P2 plus A2 into I, and A3 is equals to minus 1/3 trace of P3 into A. So in that way goes Pn equals to A into Pn minus 1 plus An minus 1 I, and An goes to minus 1 by n trace of Pn into A. So now I'm taking an example and check whether this process both, if I use the normal adjoint one, and then that normal finding out the adjoint using cofactors and finding out the determinant, and then find out the inverse of Si minus A, and then we will check with the Leverrier algorithm. Okay, so the example, so the A is the matrix that I'm considering here is minus 2 0 1 1 minus 2 0 0 0 minus 1. Okay, so first what I'm going to do, so I need to find out the Si minus A inverse. This is your objective. So what should I do? This is adjoint of Si minus A divided by determinant of Si minus A. This is basically, by definition, this is the inverse. Okay. So what I do is first take P1. I represent this adjoint using P1 S square plus P2 S plus P3 divided by SQ plus A1 S square plus A2S plus A3. Okay, so I need to find out the P1, P2, P3 and A1, A2, A3. So first what I have to do is P1 is considered as a I. Okay, so I, since A is a 3 cross 3 matrix, so I is 1 0 0 0 1 0 0 0 1, and A1 is minus of trace of A. So what are the trace? Is minus of minus 2 addition of the diagonal element. This gives 5. Okay. Now I need to find out the P2, which is A P1 plus A1 into I. So A P1, P1 is also I. So this is basically A plus A1 into I. So A is minus 2 0 1 1 minus 2 0 and 0 0 minus 1 plus A1. A1 is 5 0 0 0 5 0 0 0 5. Okay, so what you will get? This is 3 0 1. This is 1 3 0. This is 0 0 4. So this is the value of P2, and A2 is basically minus half trace of P2 into A. So first of all, for that case, you need to find out the P2 into A. So P2 into A is what is? So P2 is 3 1 0 0 3 0 and 1 0 4 into A minus 2 1 0 0 minus 2 0 1 0 4. Sorry, 1 0 minus 1. Okay. So what is the value of P2? It's minus 6 1 0 0 minus 6 0, and this is 4 1 minus 4. 4. So definitely A2, what is A2? Minus half of minus 6 minus 4, and you will get this is 12, 16, 8. Okay, so this is A2, and now I have to find out the P3. P3 is A into P2 plus A2 into I. So A into P2 into find out. First of all, A is minus 2, 1, 0, 0 minus 2, 0, 1, 0 minus 1. P2 is 3, 1, 0, 0, 3, 0, 1, 0, 4 plus A2 into I. So A2 into I is 8, 0, 0, 0, 8, 0, 0, 0, 8. Okay. So this is basically minus 6, minus 6. This is 0, and this is 2. This is, sorry, this is 1. This is minus 6, and this is 1. This is 0. This is 0, and this is minus 4. Yeah. Plus 8, 0, 0, 0, 8, 0, 0, 0, 8. What is the value I get? It's a 2, 0, 2, 1, 2, 1, 0, 0, 4. Okay. This is the P3, and I need to find out the value of A3. A3 is equals to minus of, sorry, 1/3 of trace into P3 into A. Okay. So for that case, I need to find out P3 into A. What is P3? It's a 2, 1, 0, 0, 2, 0, 2, 1, 4. And A is minus 2, 1, 0, 0, minus 2, 0, 1, 0, minus 1. So what I get is minus 4. Yeah. And this is 0. And this is 0. 2 minus 2, 0. This is 2. 2 minus 2, 0. This is minus 4. And this is 1 minus 1, 0. This is 0. This is 0. This is minus 4. So A3 is minus 1/3 of minus 4, minus 4, minus 4. And what I get is 4. Right? Plus 4. So now my SI minus A inverse. What is the first thing? First thing is 1 by S cube plus A1 S square plus A2 S plus S A3 into P1 S square plus P2 S plus P3. So this is the thing, right? So first is S cube plus what is S A1? A1 is 5 S square plus A2 is 8S plus 4. And what is P into S square? P1 into S square. So P1 is basically I, that is S square 0, 0, 0 S square 0, 0, 0 S square, right? Plus P2 into S. So what is P2? P2 is P2, every element S is multiplied with every element of P2. So this is 3S into Z, 3S 0 S, S 3S 0, and then 0, 0, 4S plus P3. P3, what is P3? P3 is 202, 121, 004. Okay. So if you do the addition, you will get S square plus 3S plus 2. Here in the middle, S square plus 3S plus 2. Here in the final, S square plus 4S plus 4. Now here is 0. Here is S plus 2. Here is S plus 1. Here is 1, 0, 0. So this is the SI minus A inverse. So here basically the calculation is not that much rigorous. So if I do the using the adjoint, if I do using this adjoint wala term, I like find out the cofactors of all the element of Si minus A and then take a determinant and then do this kind of thing. So this is okay for 3 cross 3 matrix, but when the matrix dimension is increased, this is very difficult. Now, if we see, let's see that if we do using this different method, do I get the same result or not? Okay, so it adjoint of Si minus A is basically, so first of all, write down what is the Si minus A. Si minus A is basically S plus 2, 0, minus 1, 1, S plus 2, 0, and 0, 0, S plus 1. Okay. Now adjoint, first find out the determinant. Determinant of Si minus A is basically S plus 2, 1, 0, 0, S plus 2, 0, minus 1, 0, S plus 1. What you have to do is basically the thing is S plus 2 into S plus 2 into S plus 1, because other terms are 0. So we will get only this term. So this is S plus 2 into S square plus 3S plus 2, and you will get S cube plus 5S square plus 2, 6, 8S plus 4. So you see the determinant term, this term and this term both are same. Okay. So first thing is matched. The next thing that we have to done is find out the adjoint of Si minus A. So Si minus A is cofactors of every term, right? So it's the cofactor of S plus 2 is S plus 2, 0, 0, S plus 1. This is plus, this is minus of 1, 0, 0, S plus 1. And this is plus of 1, S plus 2, 0, 0. Okay. Now the second is, if I do take this term and that term, is 0, minus 1, 0, S plus 1. This is minus, plus, S plus 2, minus 1, 0, S plus 1, and then minus S plus 2, 0, 0, 0. And the last thing is plus, is it's 0, minus 1, S plus 2, 0, minus S plus 2, minus 1, 0, S plus 1, right? No, sorry. This is not right. This is 1, 0, and the last term is S plus 2, 0, 1, S plus 2. And I have to take the transpose of this whole term. So what I will get, this is S plus 2 into S plus 1. This is 0, and this is also 0. This is 0. This term is S plus 2 into S plus 1. and this is 0. This term is s, sorry, this term is s plus 2 because minus into minus s plus 2. This term is minus of minus 1 minus 1, and this term is s plus 2 whole square. Just a minute. Yeah. So what I get, did I do the right thing? Yeah. So this is basically s square plus 3s plus 2, 0, 0, 0, s square plus 3s plus 2, 0, s plus 2 minus 1, s square plus 4s plus 4. There is something, some problematic over here. One minus term is coming. Just a minute. Yes. So what I get, s square plus 3s plus 2, 0, s plus 2, then 0, this is 0, this term is 0, I can have minus 1 over here. Okay, now this term is 0, s square plus 3s plus 2, and this is minus 1. This is s square plus 4s plus 4, and this is 0. So just check the calculation whether, I mean, the minus 1 is coming over here, I don't know, and s plus 1 somewhere I just missed out. Okay, sorry. This should be minus 1, this should be minus 1. My fault. So if this is minus 1, somewhere I just, this term should be minus 1 first, the second, yeah. I forget, this is not 0, this is s plus 1, and this term is minus 1. This term is minus 1. This term is minus 1. Everything okay. Yeah. This term is plus. This term is plus. And this one is s plus 1. If this is s plus 1, this one should be s plus 1. And this is plus. Okay. So, therefore, Si minus A inverse is basically 1 by s cube plus 5s square plus 8s plus 4 into this s square plus 3s plus 2, s square plus 3s plus 2, s square plus 4s plus 4. Here s plus 1. This is 0, 0, 1, 0, s plus 2. So these two basically the method are simpler method, but these two are basically equal method. But since here this matrix, they find out this adjoint matrix is very difficult when the system dimension is very high. So that's why it is preferable for system dimension, preferable to find out the this method if the system dimension is very high. Otherwise, you can do this kind of thing. Okay. Now the next thing is, what is state transition matrix? So state transition matrix. So how to find out the state transition matrix? Now we know the system is x dot equals to ax plus bu, right? Now if we take a, find out the solution of this equations, what we will get, xt equals to e to the power at x naught plus integration 0 to tau e to the power at minus tau b into e to the power tau d tau. This is the solution of the system. Okay. So if you know, then it's okay. If you don't know, then you will know it later. For later weeks basically. So this is the equation of the system. Now this term is known as a state transition matrix. So how to find out the state transition matrix? So state transition matrix, sometimes it is wrote as a in books, sometimes you can see this a phi of t or e to the power at, whatever it is. So this is basically the Laplace inverse of si minus a inverse. So whatever the si minus a inverse you have find out, you just take the Laplace inverse of this. So what you have to do, you just multiply this term to everything, every element, and then do the Laplace inverse. So if you know the Laplace, how to do the Laplace inverse, so you can find out the state transition matrix. So now, up to this point, do you have any kind of doubt or any kind of thing that is difficult for you to understand? So you can ask me.
Sir, in the leverage thing,
Leverage,
it like that means the value of n will be always the order of the matrix. Am I correct, na, sir?
value of
That we are having like
n. This n term, right?
yeah, n only. That is
N.
that will be order only. Correct, na, sir?
That would be the order, definitely.
Okay.
That will be the order. So it is. Do you understand that Leverrier theorem and how is it works, right?
Yeah, I am able to go through it, sir, because I need to do some more problems. Then only that much speed will be coming. I'm
Okay,
able to
okay,
get the.
okay. So anyway, I will definitely upload this notes. I mean, whatever I have discussed over here, it will upload it in a Google Drive, which is shared with you. So you can check those things over there. Okay, there is no issue. So
Okay.
So any other doubts? Any of you have any doubts? Other? If not, then I think there is nothing to discuss much for this week. I mean, this is the last thing that I have discussed. You can check the various. Look, there. Sometimes you can see. Let me just one thing that I am going to give you. Let's say. So you are asked this kind of matrix 0 0 1 0 0 0 0 1 minus 11 minus 5 minus 7 minus 2 and some x plus, I'm not writing down the b, let's say there are some b into u and you have y is equal to some c into x. Okay, so as you see, this is a 4 cross 4 matrix and don't I mean इसको देख के let's say मतलब डर मत जाना because 4 cross 4 matrix, but see, this is basically a controllable canonical form. If you see, this is basically a controllable canonical form. right? So, if you ask to find out the transfer functions of the system, you already knew the controllable canonical form. You know that the last term is basically the coefficient of the polynomial, and how this b, what is the b term, and how the c is basically the coefficient of the numerator. And from that, you can easily get the transfer function without finding out any si minus a inverse, right? I mean, you need not to find out any si minus a inverse either using the Leverriers method or using the defined adjoint wala method. So you do not need to do too much work, because it is very much easier to find, easier to see that this is basically controller canonical form. Similarly, if you ask this kind of system like observer canonical form, so you just see whether the matrix is in particular type of forms or not. Sorry, if it is in particular type of forms, so you do not need to worry about all those things. And yeah, I think there is nothing much to discuss today about. You just practice all those, how this inverse and straight transition matrix, how to find out. And if you find any kind of doubts, you can put it in a forum so that we can discuss over there. And in the next class, I will discuss about the stability of the. I think you all also the video has been shared with you. We will discuss about the Lyapunov stability and everything. So, if there is nothing to talk about, I think. I mean, do you have, since you have in no doubt, so I'm just stop recording, right? Okay.
Okay, sir.
Yeah. So another S Kulkarni. Are you listen to me? Are you listening to me?
Yes.
Yeah. I hope you have no doubt. I mean, if you have any, please ask.
No, sir. No, sir.
So I'm just stop the recording. Okay.
Okay, sir.
Okay. Okay then. Bye, and see you next week.